I'd like to recall from several times ago that function f is 1 to 1 if and only if the graph of f passes the horizontal line test. Now, if you look at the graphs of these exponential functions, like f of x equals a to the x, that meaning, in other words, f of x equals 2 to the x or f of x equals 3 to the x, any of those functions that we'd been drawing, these pass the these pass the horizontal, I mean, they do pass the vertical line test, but the key thing is they pass the horizontal line test. And so based on the thing that we said earlier, that means that a function like this is 1 to 1, right? So our conclusion here, because we have the graph of y equals a to the x passes the horizontal line test, and passing the horizontal line test, then due to this recall, means that we can say that this function is 1 to 1. So we have, for these exponential functions, we have a 1 to 1 function. Also, okay, so we just saw that the exponential function f of x equals a to the x is 1 to 1. Also, a fact about one-to-one functions, actually this is the dictionary definition of what a one-to-one function is. This property is satisfied. If f of x1 equals f of x2, then x1 equals x2. The short way of saying what's going on with a one-to-one function, I mean, I know we often think about the picture, like the horizontal line test, but what's really going on here, f of x1, that's an output, equals f of x2, that's an output, x1, that's an input, x2, that's an input. So this is really saying when the outputs are the same, the inputs are the same. So this actually, putting this all together, the fact that we have a one-to-one function here, a to the x is a one-to-one function, this creates a new technique for solving a certain kind of equation. The new technique looks like this. If you see a to the x1 equals a to the x2, then you get to set equal x1 and x2. So when you have an equation where each side is of the form base raised to an exponent, and if the bases match, you notice there's an a here and there's an a there, then you may set the exponents equal. So you notice this exponent of x1, this exponent being x2, they're just set equal here. You have x1 is equal to x2. So you got to have matching bases for this to work. Okay, so we cite the new technique here up at the top, and let's solve the equation 4 to the power 7 minus 2x equals 4 to the power 1 plus x. Notice the bases are equal. They're both 4s. In this case, in this example problem, to apply the technique, a is 4. A is 4 here, a is 4 there. And so we get to set the exponents equal. We set 7 minus 2x equal to 1 plus x. Now, add 2x to both sides. So you have 7 equals 1 plus 3x. Subtract 1 on both sides. You have 6 is equal to 3x. Divide by 3 on both sides. And you have 2 is equal to x. Okay, we're done with this problem, but an important comment is in order. With the original equation at the top that says 4 to the 7 minus 2x equals 4 to the 1 plus x, it is a very common habit for people to want to cancel the 4's. So again, what just happened was we could turn the equation that we were given into 7 minus 2x equals 1 plus x due to the matching 4's. But because it looks like we're canceling 4's, people will draw slashes through the 4's. Please do not draw lines through the 4's. I promise you can go from 4 to the 7 minus 2x equals 4 to the 1 plus x, and on the next line down, you can write 7 minus 2x equals 1 plus x without putting any diagonal slashes through the 4's. Just don't do it, right? So why not draw slashes through the 4's? It looks like the 4's are canceling. The reason why not is it leads to a misconception about a future topic. So really, what's going on is we're just using this new tool up here. The tool says if the bases are equal, you may set the exponents equal. That's all we're doing. So we set 7 minus 2x equal to 1 plus x. So you can take the given equation and write as your first line of the answer 7 minus 2x equals 1 plus x without drawing any slashes through the 4's. Just really try it. Like literally write this, no slashes, write that. Have no slashes through. Build a good habit now. There's something related to a misconception, a mistake that happens later that I'm not going to dig into right now. Let's try applying the new technique again. Okay, so again, if the bases match, we can set the exponents equal. Take a look at this equation. We have a base of 9 on one side, we have a base of 9 on the other side. Now, without drawing any slashes through the 9's, we'll set the exponents equal. So one exponent is x minus 2 times x plus 3. The other exponent is 2x squared minus x minus 14. Now, I know this equation looks funky, but you've got to step back for a moment. We now have many techniques for solving equations. So look at it and go, you know what? this is actually a quadratic equation. I know it doesn't look like a quadratic equation, but if we were to distribute on the left side, we'd have quadratic. Yeah? You've got this um, x squared plus x minus 6, and if we collect terms on one side and so on, we're going to have 0 is equal to x squared minus 2x minus 8. So that's the foresight that is important to try to build by always asking yourself when you have an equation, before just doing whatever, is asking yourself what kind of equation do you have. And here, looking 2 steps ahead, we say, oh, if we had FOILed this out, the highest degree is a 2, right? The highest exponent you'll see is the number 2, degree 2. So this is quadratic, and so we have an exit strategy that, we're going to take the quadratic and either factor if possible, or we can always complete the square. It turns out this one will factor. X minus 4 times x plus 2 equals 0. Now we apply the zero product property. So each factor individually is set equal to 0. So x minus 4 equals 0, or x plus 2 equals 0. We can add 4 on both sides of the first equation. We can subtract 2 on both sides of the next equation. So x equals 4 or x equals negative 2. Again, please do not put a slash through the 9s. It's so tempting to just want to draw a line through this 9 and a line through that 9. It causes misconceptions. People start thinking all kinds of things like 9 times x minus 2 times x plus 3. But it's not. It's 9 to the power x minus 2 times x plus 3. Okay, let's also note that this new technique, it does not apply to the equation 5 to the power absolute value of 4x minus 2 then times a 5 equals 5 to the 11. And the reason is because the left side here is not just a base to an exponent, but there's this extra 5 that's right here. There's this extra times 5. So to solve this equation, we can't apply the new technique, at least not right away. We're going to have to do something about the fact that the left side is base exponent times another thing, times this 5. Well, we can rewrite the left side as 5 to the power absolute value of 4x minus 2, close absolute value, then plus 1, and that plus 1 is still inside the exponent. This is just making use of an old exponent law that when you're multiplying things with the same base, you add the exponent. So the exponent of the exponent which was absolute value of 4x minus 2 is added to the exponent which is the hidden 1. Okay, now the shape of the problem is there's a single base and single exponent on each side. I mean, the exponent's a big mess, but it's base raised to an exponent equals base raised to an exponent on each side. And luckily, the bases match. We have a base of 5 on each side, so we can set the exponents equal. Again, no slashes through the 5s. But now we have absolute value of 4x minus 2, close the absolute value, then plus 1 is equal to the other exponent, which is 11. Now, let's subtract 1 on both sides. Now we have an absolute value equation. It will help if we substitute the contents inside the absolute value. So let's have u is equal to 4x minus 2 so that our problem turns into absolute value of u is equal to 10. There are two solutions for u. So u equals 10 or u equals negative 10. Notice this line here does not have absolute values anymore. We've processed what the absolute value does. We've determined what values u could be so that the absolute value of u is equal to 10. Now that we have solved for u, we have u equals 10 or u equals negative 10, we can substitute 4x minus 2 for each u. Then we add 2 to both sides of both equations and divide by 4 on both sides of both equations, and we have x equals 3 or x equals negative 2.